Okay, so in this video, we're going to go through and do some practice picking which atom or ion fits the particular trend, and then also using our justification methods that were in the last video, the Zeph, the shielding, and the distance, to better explain, or say properly explain, what our choices are and why. So for the first one, we're going to look at select the atom in each of the following groups that is going to be the smallest. Anytime we say smallest without any other information, it has to be size. So remember what your size trend is. Your size trend is, as I go down a group, my size increases. As I go across a group, across a period, my size decreases. So as I go down, we're going to increase because we're adding layers upon layers of electrons. As I go across, I'm going to decrease because the positive pull of the nucleus, the Zeph, right, the effective nuclear charge, is going to increase. And as the nucleus gets bigger, but the electrons don't get any further away, they get pulled in just a little bit more tightly. So the first one we're going to look at and compare is calcium, strontium, and zirconium. So let's find those three on the periodic table. So calcium, strontium, and zirconium. So this little corner here. So one of the first things that you need to notice is that both zirconium and strontium are together on the same horizontal period, and calcium is one level higher. And so we need to look at how that plays into our trend. So our trend is, as we go down, we increase. So as we go down, we're adding layers of electrons. Well, even if you just compare the atomic number here, which we know in an atom represents both protons and electrons, 20 protons and electrons, 38 and 40. Obviously, 38 and 40 is going to be more. They're going to be bigger. So calcium is going to be smaller by sheer fact that it has the fewest number of electrons. Okay, so how do I justify that? It's an up and down justification choice. So my choices are going to be shielding or distance. You could really go either way with this one because it is size. I would say that maybe distance is a little easier to use, less wordiness required because I'm not asking about energy. If it was energy, I would definitely go shielding. But because this is size, up and down, distance will get everything done that you need. So calcium is the smallest because the distance from the nucleus to its outermost 4s electron is less than either strontium or zirconium. Good enough. All right, let's look at the next one. SP and Si. So sulfur, phosphorus, and silicon. So sulfur, phosphorus, and silicon are all here in the same horizontal row. It's a left and right decision. Remember that our trend is, as we go across, we decrease. So we're going across. We want to know which one's the smallest. So as we go across, sulfur is going to be the smallest. Then we need to justify it. Well, this is a left and right choice. With a left and right choice, the only justification I can use is Zeph. So sulfur small, and we need to use Zeph to explain it. Sulfur has the largest Zeph, or you could also say the largest, most positive nucleus. Therefore, it holds the electrons more tightly and is smaller. Okay. All right, so 2 down, a couple more to go. Select the atom with the lowest electronegativity. So remember, what is electronegativity? When we're looking at electronegativity, we're looking at the ability to attract a shared pair of electrons towards one's own nucleus. towards one's own nucleus. Who is going to be greedy and hold on to those electrons in a shared covalent bond more tightly? Okay. So we're going to look at our trend overall. Because as we go across, we increase. As we go down, we decrease, right? It's the opposite of the size trend because the distance from the nucleus to the outermost electron plays a role in this. So let's compare where these are on the periodic table. So we've got copper, we've got silver, and we have gold. No, I'm sorry, with copper, silver, and zinc. So which one of them has the lowest electronegativity? So the lowest electronegativity is going to be the one that is the largest in size because it's not going to be able to pull those electrons near as tight. So the largest in size is going to be silver because it's furthest down, right? More layers of electrons. The nucleus is more shielded, so it's not going to be able to pull the electrons in very tightly. So silver is going to be our choice here. Okay. So how do we justify this? Well, it's up and down. We're using shielding. You can start by talking about the size of them, and that plays into shielding, which then will explain the electronegativity. I think that's probably the best way to attack this if it's me. So I would say silver is the largest atom. Therefore, its outer electrons are most shielded from the nucleus, which has a weak pull on the bonded pair. Okay. So it has the lowest electronegativity. Okay. Select the atom with the lowest ionization energy. Well, remember that ionization energy is going to follow the same trend that we see here for electronegativity. So oxygen, fluorine, and chlorine. So this little corner right here. Who's going to have the lowest electronegativity? I'm sorry, it's not electronegativity, it's ionization energy. Who's going to have the lowest ionization energy? So ionization energy, as I go across, it increases. As I go down, it decreases. So the lowest one is going to be the chlorine. It's an up and down choice. So again, we need to look at shielding. Okay. So chlorine has the lowest ionization energy because it has the highest shielding. The outermost electrons are protected or shielded from the pull of the nucleus and are easiest to remove. Or also, I would say maybe require the least amount of energy to remove. Least amount of energy to remove is a better way to wrap that up. I ran out of room, or I would rewrite it. Okay. Select the atom with the lowest ionization energy and justify between phosphorus, sulfur, and chlorine. So phosphorus, sulfur, and chlorine is in this one horizontal group, and I want the lowest ionization energy. So in terms of lowest ionization energy, as we go across, it increases. So if we were following the trend, we would say that phosphorus has the lowest ionization energy. But what do I remember here? P3, P4 exception. So because of the P3, P4 exception and the paired electron in the sulfur, it's actually going to be sulfur that has a slightly lower ionization energy. So I need to make sure that I reference that correctly. Sulfur has the lowest ionization energy because its paired electron experiences electron repulsion and therefore is easiest to remove. If all you say here is, oh, it's because of the P3, P4 exception, you don't get credit for that. What does that even mean? You have to actually explain it, okay? All right, so the last ones we're going to look at are dealing with atoms and ions. So there's just a kind of a variety here. There's not really a hard and fast rule for justifying these ones. A lot of times with these, I look at proton to electron ratio. So that's how I'm going to show you most of these as we go through. So select the atom, or select the particle that is the smallest. So calcium and calcium plus 2. So with calcium and calcium plus 2, let's look at our protons and electrons. So calcium has 20 protons and 20 electrons. Calcium plus 2 has 20 protons and 18 electrons. Okay, so I can look at this and say, well, if I think about my tug-of-war analogy, the protons in calcium plus 2 have a distinct advantage. So they're going to be able to pull this nucleus or pull those electrons towards the nucleus more tightly. What you absolutely cannot say here is anything about Zeph. Okay, reason being is these two things have the exact same nucleus. They don't have any difference in Zeph. They have the exact same effective nuclear charge. They both have 20 protons. So you have to talk about the difference in protons and electrons when you are justifying this, when you are explaining this. So with 2 more protons than electrons, the calcium plus 2 is going to be able to hold those electrons in more tightly and then be smaller. Right? Fluorine minus 1 and chlorine minus 1. So fluorine minus 1 and chlorine minus 1, they both have the same charge, but when you look at their positions on the periodic table, when fluorine takes on 1 electron, it has 10 electrons. When chlorine takes on 1 electron, it has 18. 18 is still way more than 10. 18 electrons will always be bigger than 10 electrons. You have a whole nother layer of electrons in chlorine than you do in fluorine. So fluorine is going to be by default smaller. It has fewer layers of electrons, and that's what I would say if you had to justify this. Fluorine minus 1 has less layers of electrons than chlorine minus 1, and therefore is smaller. All right, magnesium plus 2 and beryllium plus 2. So magnesium and beryllium, same situation kind of with fluorine and chlorine, vertical column. Beryllium plus 2 has lost 2 electrons. Magnesium plus 2 has lost 2 electrons. So beryllium has 2 electrons and magnesium has 10. 2 is still smaller than 10, right? So beryllium by default, even though it's a positive ion, is still going to be smaller than magnesium. That's likewise a positive ion because it has fewer electrons. So beryllium plus 2 is going to be smaller. All right, and then the last one here, silver and silver plus 1. Same type of scenario we had up here with calcium and calcium plus 2. 47 protons, 47 electrons, 47 protons, 46 electrons. We have a difference here between protons and electrons. The protons are going to be able to pull a little bit more tightly, therefore the positive ion is smaller. And I'm just going to throw one more in here, kind of last ditch for good measure. Let's look at oxygen and oxygen minus 2, just so we have one example going the other way. So oxygen has 8 protons and 8 electrons. Oxygen minus 2 has 8 protons and 10 electrons. Now when I'm looking for the smallest, because this has 10 electrons, they're going to be able to spread out more because they have outweighed the protons. So in this case, it's the atom that is going to be smaller than the ion. Because remember, negative ions are large because they have additional electrons. Positive ions are small. Okay, hopefully that helps with your practice with justifying and periodic trends. And if you need more help, feel free to message me.